In this tutorial, we're looking at Lchl Higher Level 2023, Paper 1, Question 3. In the first part of this question, you're asked to prove that root 2 is not a rational number. This is one of our proofs from Paper 1, so I'm linking you the tutorial from the course and you can have a look now. Okay, in this video, we're going to talk about one of the proofs that can come up in Paper 1. You could be asked to prove that the square root of 2 is an irrational number. And this is the only example that we're going to see of a proof by contradiction. A proof by contradiction is you prove that something is true by you assume the opposite and then you prove that's false. So what I'm going to do in this proof is I'm going to assume that the square root of 2 is a rational number. And then I'm going to prove that that's actually false. If I can prove that it's not a rational number, then obviously it must be an irrational number. So it's important, just make a note that this is the only example you're going to see of a proof by contradiction. So let's just first of all consider the definition of a rational number. Okay, so just let's remind ourselves of the definition of a rational number. A rational number is any number that can be written as a fraction in its simplest form. So in other words, it has to be written in the form of a over b, where a and b are elements of z. So the top of the fraction and the bottom of the fraction need to be integers. But what I want to focus on is the fraction needs to be in its simplest form. And what that means is, like for example, 7 over 5. 7 over 5 is a fraction in its simplest form. So that's a rational number. And it's in its simplest form because it can't be simplified. Like I can't write it as 10 over 8. 10 over 8 is a fraction, but it's not in its simplest form because both 10 and 8 are 2 divides into both of them. So in fact, if I wanted to write this fraction in its simplest form, it would be 5 over 4. A fraction in its simplest form needs the top of the fraction and the bottom of the fraction don't have any common factors other than 1. The only number that will divide into both 7 and 5 is 1. The only number that will divide into both 5 and 4 is 1. I want you to just bear that in mind because it becomes important when we get to the end of the proof that we're about to look at. So let's now start off by having a look at how to prove that the square root of 2 is irrational. In this proof, the maths is going to be quite straightforward. It's just very, very obscure. So we have to use proof by contradiction in order to prove that the square root of 2 is irrational. So basically, the first thing I'm going to do is I'm going to assume that the square root of 2 is rational. And now I'm going to prove that that's impossible. So in order to assume that a number is rational, I'm assuming that it can be written as a fraction in its simplest form, where the top of the fraction and the bottom of the fraction are integers. And I'm assuming that the biggest number that will divide into both a and b is 1. So if I'm going to assume root 2 is rational, we start off mathematically by saying that the square root of 2, it can be written as just a over b. And a and b are elements of z. So I'm just basically starting off, obviously in order to fully understand that, we needed to look at the definition of a rational number first. Now in the next few lines, we're just going to try and simplify this. If I wanted to simplify this fraction, or this equation, probably the first thing we might look at is to try and eliminate the square root. In order to eliminate a square root, you simply square both sides. If I square the left-hand side, root 2 multiplied by root 2 would just give me 2. And if I square a over b, I would simply get a squared over b squared. So all I've done there is I've simplified it by squaring both sides. And now what I might want to do is eliminate the fraction. In order to eliminate the fraction, I'm going to multiply both sides by the denominator of the right-hand side. In other words, multiply both sides by b squared. If I multiply the left-hand side by b squared, I get 2b squared. And if I multiply the right-hand side by b squared, I get a squared. Now, it's the next few steps here. This is the obscure stuff that tends to throw people off. Let's just focus first of all on the left-hand side. I have 2 times b squared. And for the moment, I don't know what b squared is. It could be, b could be 7 or 10, it could be -2 or -5, it could be any whole number, because I know it's an integer. But I know for certain that any number multiplied by 2 has to be even. Because there's a 2 in front of the b squared, it is definitely the left-hand side is definitely even. So I can say that 2b squared is even. I don't have to explain that. That's just it's logical. Any number, any whole number multiplied by 2 is definitely an even number. Now 2b squared is equal to a squared. So if I can say that 2b squared is even, then a squared obviously needs to be the same as that. Like if this is a 10, then the right hand side needs to be a 10. If it's 14, it has to be equal to 14. So if 2b squared is even, I can also then conclude that a squared is even. Now, so I think usually students have no problem with that. It makes perfect sense that a squared is even. But now it's the next thing that tends to catch people out. If a squared is even, then that also means that a has to be even. I can conclude that a is even. Okay, in order to think about this one, like first of all, I definitely know that a is a whole number, which means that a squared has to be a square number. In other words, it has to be something like I can guess 16 because I'm able to get the square root of 16, or it could be 36 because I'm able to get the square root of 36, or it could be 64 because I'm able to get the square root of 64, or so on. It could be 100 because I can get the square root of 100, or 144. Basically, I know a squared is even, but more importantly, I know that a is a whole number. So I can definitely get the square root of a squared and say that it's a whole number. And if the original one I'm starting off with is even, then the square root of it also has to be even. The square root of 16 is equal to 4. The square root of 36 is equal to 6. The square root of 64 is equal to 8. Notice that all of these answers, all of the square roots are also even. Let's just consider what would happen if I took an odd one. An example of a number that has a whole number square root is 9. If I got the square root of 9, that would give me 3. So the square root of an odd number gives me an odd number. If I continued on, 25 is another odd number, and the square root of 25 is 5. Basically here, if a squared is even, then I can conclude that the square root of it will also be even. Now you don't need to write any of these in your proof. I just wanted to show you the general trend, because essentially it's those three lines that tend to confuse people. I relatively easily got to this point, but from here I can say that 2b squared is even, which means that a squared is also even, which means that a must also be even. If a is even, then that means it can be written as 2 times another number. Let's just take, for example, the first even number is 2, and I could write that as 2 multiplied by 1. The second even number is 4, and I could write that as 2 multiplied by 2. The third even number is 6, and I could write that as 2 times 3. Or 8, I can write it as 2 times 4. Now, I don't know what a is, but I know a is definitely an even number. So all of the even numbers can be written in this form, which means that I could say that a can be written as 2 times k. I just don't know what k is. But essentially, just from getting to this point, I can now deduce that a can be written as 2 times k, where k is also an integer. Remember, all we're talking about here are whole numbers. So that's the next thing. Again, you don't actually need to write all of that, but what you need to do is just conclude that a can be written in the form 2 times k, where k is also an integer. K is a whole number. So that's the really obscure things. If you're not 100% sure on that, maybe just rewind this and just watch my explanation again. Simply from getting to the point that 2b squared is equal to a squared, I can conclude that a must be even, and that, in other words, it can be written in the form of 2 times another whole number. So what I'm going to do now is I'm simply going to go back to the main body of my proof and I'm going to sub it in. Instead of an a, I can sub in 2 times k. So in this case, the left-hand side I'm going to keep it exactly the same, but the right-hand side, instead of a, I'm going to sub in 2k. So a squared becomes 2k to be squared. Now let's just simplify this a little bit and see where we get to. So the left-hand side stays the same. 2k multiplied by 2k gives me 4k squared. Now in order to simplify this, I can divide both sides by 2. And if I divide both sides by 2, I can say that b squared is equal to 2k squared. Now this is the really interesting bit. Notice the similarity between what I have here, 2b squared equals a squared, and what I have here, 2k squared equals b squared. from this line, remembering that k is a whole number, I can say that obviously 2k squared is even. 2k squared is definitely even. And 2k squared is equal to b squared. So if 2k squared is even, I can conclude that b squared is even. And based on the logic that we used up here, if b squared is even, I can also conclude that b is even. Now, this is where the problem lies. Up here I was able to conclude that a is even. And down here I'm able to conclude that b is even. And essentially that's all that we need for the proof. The very start, and the very first thing we did here was we assumed that the square root of 2 is a rational number. If the square root of 2 is a rational number, then it could be written as a fraction a over b. But that fraction needs to be in its simplest form. However, I'm after concluding that the top of the fraction is even and the bottom of the fraction is even. That means that the fraction is not in its simplest form. Look back at the example I did in the previous slide. I used, for example, 10 over 8. The top was even and the bottom was even, so it could be written as 5 over 4. So I'm just going to wipe this out and make our conclusion here. But essentially it's just on the premise that if the top of the fraction is even and the bottom of the fraction is even, then the fraction is not in its simplest form. So I'm after proving that the first line here is impossible. It doesn't make sense. The square root of 2 cannot be written as a fraction in its simplest form. So all the maths I did there has proved that a and b are even numbers. So that means that a over b is not in its simplest form. The square root of 2 can't be written as a fraction in its simplest form. So therefore I can conclude that the square root of 2 is not rational. My original assumption was incorrect. If the square root of 2 is not rational, then it must be an irrational number. So I'd say this proof is probably the most obscure proof. It's worth your while looking at it once or twice because it is quite short. And if you look back in exam questions, it has come up a few times. So I think it's important that you're clear on and you fully understand this one. In part B, we're dealing with logs. And essentially we're being asked to change the base of certain logs. The content here we've covered in indices and logs 4. And the formula we're going to use here are available in your maths tables on the logs page. So essentially here we're given a log t to the base 3, to the base 9, to the base 27, to the base 81, and we know that it's equal to 10. We're given a hint that we should change the base in order to try and find the value of t. Now you should recognize that it's easiest to change them all to the lowest base. So we're going to change the log to the base 9 and 27 and 81. We're going to turn them all into log to the base 3s. It's an easy enough formula to use. If you've log t to the base 9 and you want to turn it into a log to the base 3, you just come up with a fraction. The top is a log to the base 3, the bottom has a log to the base 3. The small subscript number, which was a base, goes on the bottom, and the other number, the t, goes on the top. Basically, I just did that 3 times. I changed the base 3 times. And then you should recognize, or you can plug it into your calculator, log 9 to the base 3 is 2, log 27 to the base 3 is 3, log 81 to the base 3 is 4. Another way of looking at that is, this is actually the same. This is a half log t to the base 3, this is 1/3 log t to the base 3, and this is 1/4 log t to the base 3. Now on the left hand side we've all like terms. So I just plug into my calculator 1 plus a half plus a third plus a quarter. That adds up to 25 over 12. So I have 25 over 12 log t to the base 3. Okay, so taking it from there, all I decided to do now is divide both sides by 25 over 12. 10 divided by 25 over 12 is 24 over 5. Now you need to go to your maths tables on page 21 and look at the very first rule of powers, the very first rule of logs that we studied. The very first rule of logs that we studied told us that the base to the power of the answer, or the right hand side, is equal to the larger number in the log. In other words, if log t to the base 3 equals this, I can say that 3 to the power of 24 over 5 is equal to t. And that's my final answer. The question asked you to leave your answer t in the form 3 to the power of or, where or is a rational number, or an element of q. And that usually indicates that it's going to end up as a fraction. Usually if you see or an element of q, you're expecting or to end up being a fraction. In C part 1 here, we're asked to explain what log m to the base 6 means. Well, log m to the base 6 means to what power must I raise 6 to get m? In other words, 6 to the power of what will give me m? If you're struggling to figure out what I'm talking about there, let's look at a simpler example. Let's take, for example, log 8 to the base 2. Log 8 to the base 2 is equal to 3. Because if I was trying to describe in a sentence what this is, it's asking to what power must I raise 2 to give me 8? And the answer to that question is 3. 2 to the power of 3 will give me 8. Likewise, if I was trying to describe this, I'd say, to what power must I raise 6 to get m? So 6 to the power of what will give me m? That's the sentence that you should have come up with in the exam. In C part 2, we're told that m is a real number and m is greater than 6. And we're asked to explain what does that mean in the context of log m to the base 6. Well, based on what we said in part 1, I know that log m to the base 6, I'm asking myself, 6 to the power of what will give me m? So let's consider what will happen if m was actually equal to 6. If this was log 6 to the base 6, then I would say that 6 to the power of 1 gives me 6. So if m is equal to 6, then that means that log m to the base 6 would be equal to 1. But I'm being told that this number has to be bigger than 6. Like, for example, if m is bigger than 6, maybe it's a 36. If m is 36, then 6 to the power of 2 gives me 36. So if m is 36, then log m to the base 6 has to be equal to 2. So in other words, if m is greater than 6, then log m to the base 6 has to be bigger than 1. Because if it was actually equal to 6, then log m to the base 6 has to be equal to 1. So obviously as m gets bigger, the value of the log gets bigger as well. So this is what they're looking for here. Because I know that m is bigger than 6, that means that log m to the base 6 is bigger than 1.